Okay, today is 4/1/19, and I have failed utterly. I didn't do anything remarkable for you. I'm so sorry. I feel like an abysmal failure. So you know that kinetic means motion, and kinetic energy is the energy of something in motion. Now, the thing is, energy is the ability to do work. That's handy. That's going to come up again. So work means we're applying a force and actually moving something. Kinetic energy is the ability of a moving object to move something else. Who here has gone bowling? Excellent. If not, you're going to have homework. Oh, we should totally adjourn and go to a bowling alley right now. Let's do this. They won't mind, right? It's April Fool's Day. Anything can happen. So why does that ball move the pins? Because it has kinetic energy, and it's able to transfer that kinetic energy and do work on the pins and move them, unless you hit it in the gutter like I do. Okay, so we're going to go through all the derivations, because I do feel like that makes the math under it make more sense. We're going to start off with the easy one. Energy is the ability to do work. You know that. We've talked about that. You had that in physical science. And you actually should have had this equation in physical science. 1/2 mass times velocity squared is the kinetic energy of any object. So Ke equals 1/2 mv squared. Based on that, and when you think about what they were discussing in the NOVA special on the space shuttle, which factor is more important, mass or velocity? Looking at that equation. Velocity. It's squared. And back when I used to show these on actual PowerPoint, you know, this would come up first and then this would pop up after you figured it out, but the answer's right there. Oh well. So yeah, the velocity is much more important. The old trope about a penny dropped from the top of the Empire State Building could kill someone may not be true, but we could figure it out. We could actually compute that. Oh, we should do that sometime, huh? Because it's not the mass that matters, it's the velocity. It's not the mass, it's the velocity. This is so ridiculously easy, I could train chimpanzees to do it. So we're going to do the 5B sample problem together, and then we'll do the 5B practice problems. They are all assigned. And speaking of bowling, 7-kilogram bowling ball moves at 3 meters per second. How fast must 2.45-gram table tennis ball move in order to have the same kinetic energy as the bowling ball? Is this speed reasonable for a table tennis ball in play? So, what we're interested in is the Ke of the BB, Ke of the bowling ball, and we want to compare it to the kinetic energy of the ping pong ball, Ke of PP. We're told that mass of the bowling ball is 70 kilograms. Mass of the ping pong ball is 2.45 grams, so 2.45 divided by 10 to the third kilograms. Oops, sorry. Velocity of the bowling ball is 3.0 meters per second. I'm going to set all the stuff about the ping pong ball down there for a second. Move this up here. So, kinetic energy of the bowling ball equals, well, first, let's write this out. Mass, 1/2 mass of the bowling ball times velocity of the bowling ball squared. 1/2 m. And I stand corrected. I wrote 70 kilograms. It should be 7. A 70-kilogram bowling ball is like throwing a 7th grader. You know, and if you've hung out with 7th graders, you might want to, but it's a heavy bowling ball. Okay, so 7 kilograms, that's better. That's like a 14-pound bowling ball, and that's a reasonable bowling ball, if a bit heavy. So Ke equals 1/2 mass velocity squared. Let's plug in our... Okay, so we've got our plugins done. We find that the kinetic energy of the bowling ball is 31.5 meters per second, meters squared per second squared, meter squared kilograms over second squared. What? Look at the units for kinetic energy. Joules. Yeah. And 1 joule is 1 meter squared kilogram over second squared. It's the same units we use for work, which is kind of weird, but energy is the ability to do work. So that's basically how much work you could do with that amount of energy. So we'll get rid of that and just put in joules. So we've got 31.5 joules, which is not unreasonable. Now let's see how fast the ping pong ball would have to move in order to have the same amount of energy. Okay, so kinetic energy of the ping pong ball equals 1/2 mass of the ping pong ball times velocity of the ping pong ball squared. Let's do the plug-in. Geez Louise, what am I doing? I'm inserting things before I've rearranged. So we're solving for velocity. So to do that, we got to do some rearrangement. 2 KE ping pong divided by mass of the ping pong ball gives us velocity of the ping pong ball squared, which means taking the square root of both sides will give us the equation we need for the velocity Gesundheit. Okay, plug in. Now here's the question. What kinetic energy are we using? Yeah, we want it to match the kinetic energy of the bowling ball. So 31.5 joules divided by 2.45 times 10 to the negative third kilograms square root gives us the necessary velocity for the ping pong ball. Okay, so 160.3567, etc. meters per second for the ping pong ball. Is that a reasonable velocity for a played ping pong ball? No, not at all. What is that in kilometers per hour? You know, this is basically you in your rocket car going from here to Pittsburgh in 10 seconds. Not going to happen. So not at all a reasonable velocity. Mass does matter, even though velocity matters more. Your mission, whether or not you choose to accept it, are these, and they're ridiculously easy. So I'll give you the rest of this period. You can probably finish them all, and then we'll move on to tying together kinetic energy and work done.